Okay. Is a molecule SF4 polar or non-polar? So for this one, actually, SF4, we're getting a lot of polar, non-polar practice. This is good. Polar or non-polar for question 17. So the first thing I recommend again is to draw that Lewis dot diagram. And since luckily we just did sulfur, you can literally just say it again that it's neon 3 S2 3P4. That's 6 electrons in total. Okay, and now fluorine starts at helium and it's just 2p 2p5. Okay, and that means 7 electrons. So for sulfur tetrafluoride, the reason why we say it like that, because as you remember, it's 2 nonmetals bonded together, so this is a covalent compound, right? And for the rules of covalent compounds, you need to include the prefix. So yes, the name actually is sulfur tetrafluoride, not chloride. Fluoride. And they still follow the same rule that the I guess the second part of it has to still follow the IDE. You drop the fluorine INE, the ending, to replace it with a new suffix, the IDE. So 6 electrons here, 7 times 4, so that's 28 plus 6. In total, that is 34 electrons. Okay, I'm actually going to use a calculator to make sure. 7 times 4 plus 6, 34. Perfect. So for this, I like to still follow the rule of putting the sulfur in the middle. Okay, surrounded by fluorines. Now remember that sulfur, just like phosphorus actually, is one of the other ones that like to break the octet rule. It doesn't really care about that. So let's put the fluorines out there. So using the same concept though, okay, we have now, it's sharing one of its electrons, so 2, 3, 4, 5, 6, 7. Fluorine is good. 7, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay, so of the 6 electrons sulfur has, it's sharing 4 of them, so it still needs 2 more. So you can just put it right there. Okay, so let's count. We have 8, 12, oh wow, 8, 16, 24, 32, and then plus those 2 red ones right there, 34. Perfect. And if we did the actual electron number, we have 6 minus we have 2 valence, and then it's 6 being shared over 2. Oops, I think I might have done the math wrong. It's not 6 being shared, it's 8 being shared, sorry, because it's 8 electrons being shared in total. So 2 plus 4, that's equal to 6, so it does equal 0. Same thing with the fluorine. 7 minus it has 6 in the lone pairs, so 3 lone pairs of 2, so that's 6 in total, and then plus 2 over 2, that is 7, and then that also equals 0. So that's good. This is actually what sulfur tetrafluoride would be. Now to answer if it's polar or non-polar, this is your answer right there. Okay, not only does it have a lone pair on the sulfur, it's not counterbalanced by another lone pair. So if we were to actually draw it, it would look something like this. And so first of all, not the molecular, the bond number, actually, yes, that's the number, that's what I was looking for. The bond number would be 4 bonds, okay, that's what it has with sulfur, plus that 1 lone pair. So the bond number for sulfur is 5, okay. That means, okay, well, not even there yet, but it has 4 bonds and 1 lone pair. So I'll actually show you the official geometry, but this is what the drawing would typically look like when you actually draw sulfur. Okay, the electron will be kind of a jerk doing that. and then we have the other two kind of sticking like that. Okay, so with this, these angles here from the top to the bottom, like pictures kind of like this. It's kind of like a circle with a line through it. Okay, that's what it looks like. As in, this is where the electron would be, this is where the first bond would be, and this is where the second bond would be. Let me draw a different color. So it's like into the 3D molecule. If you're looking at it from like the side, okay, this is where the first fluorine would be, second fluorine, third fluorine, fourth fluorine up here, and then the valence shell. So when you draw like this, though, you can kind of see it. But exactly, the point being, right, is that these bonds here between the fluorines, because the electron, the lone pair has so much push, these bonds are just slightly, well, not slight, but just less than 120, okay, degrees in terms of that, I guess, pi. It's not a perfect split pi, and because this thing is also pushing these fluorines to the top, these angles here, they're not actually 90 degrees, sorry. They're actually going to be just less than 90 degrees, because it's kind of just pushing everything to where everything kind of, so it used to be straight, right? But the electrons, the lone pairs are pushing to where it kind of bends like that, and then these ones that are here, like this, kind of bend like that, as in they get close together. So that's the shape we have there. I don't know the actual shape name, but point being is that because now we've drawn it like that, you can see clearly that this double bond here, I mean not double bond, lone pair, has such a electronegative force, because that's like the strongest you can get. It's the electron itself, to where it kind of just pulls everything that way. Okay, that wins a tug of war. So that's what's happening there. Because there's a lone pair there, everything is thrown off balance, making this molecule, the answer is that it's going to be polar. Okay, so let's look at that with the actual Vesper theory. As I mentioned, it was bond of group of 5, and we scroll down to 5 here, 4 bonding groups and 1 lone pair. So it's known as trigonal bipyramidal, and it's known as seesaw. So with that being said, exactly, this is what it would look like. As I said, it's going to be a little bit less than 120, because I think this is a better picture. You see here, the bottom parts, they're actually a little bit less than 120 degrees apart, because how strong the electron is. And then the 90 degrees here, it's actually a little bit less than 90 degrees, because that's how strong exactly the electron lone pair is. So in total, it is going to be polar, though. And just like that, perfect. It even shows nicely the, I guess, the bond lengths. So exactly, it's from F to F, exactly. It just shows the total thing. So 173.1 degrees. I mean, if you were to split it in half, you know that each part, when it goes from F to like the middle, is less than 90 degrees. Okay, and this one as well, showing that the circle part is 101.6, which is indeed also less than 120 degrees. So it does say sulfur tetrafluoride is a polar molecule. So this is correct. So let's move on to question 18. Oops.